Welcome to this presentation on boot integrity and secure storage in mobile devices. In today's digital world, smartphones and embedded systems store massive amounts of sensitive information, including personal data, financial details, and corporate credentials. Because of this, attackers increasingly target the earliest stages of a device's operation, the boot process. Boot integrity ensures that when a device powers on, only trusted and verified software is executed. Without this protection, attackers could insert malicious code, install persistent malware, or gain complete control over the system before the operating system even loads. Along with boot integrity, secure storage technologies protect sensitive data and cryptographic keys from unauthorized access or modification. In this presentation, we will explore how modern systems establish a chain of trust, enforce secure boot mechanisms, use authenticated boot for measurement and attestation, and protect sensitive data using hardware-backed secure storage. Boot integrity is the foundation of device security. It ensures that every piece of software executed during startup is authentic and has not been modified. The goal is simple but critical: prevent attackers from running malicious code during system initialization. Without boot integrity, attackers could install bootkits, rootkits, or firmware malware that operates below the operating system and remains extremely difficult to detect. One important concept behind boot integrity is the chain of trust. The chain of trust begins with a hardware root of trust, often stored in immutable hardware such as ROM or security fuses. This root component contains trusted cryptographic keys that cannot be modified remotely. From there, each stage of the boot process verifies the next stage before executing it. If any stage fails verification, the boot process stops immediately. This layered verification ensures that every component of the system startup is trusted. Secure boot is one of the most widely used mechanisms to enforce boot integrity. Its main purpose is to ensure that only digitally signed and verified software components can run during the device startup process. The process begins with the boot ROM, which is stored in immutable hardware. This component contains the public keys used to verify trusted firmware. Next, the boot ROM verifies the first stage bootloader, also known as FSBL or SPL. This bootloader performs initial hardware configuration and prepares the system for the next stage. After verification, the first stage bootloader loads the second stage bootloader, which provides advanced system initialization and prepares the operating system kernel. At every stage, digital signatures are verified using cryptographic algorithms. If verification fails, the system will halt the boot process. Depending on the platform, the device may enter a restricted recovery mode, display a security warning, or refuse to start entirely. This strict verification process prevents unauthorized or malicious firmware from running on the device. While secure boot prevents untrusted software from executing, authenticated boot takes a different approach by measuring system integrity rather than blocking execution immediately. In authenticated boot, each stage of the boot process calculates a cryptographic hash of the next component before loading it. This hash, often generated using algorithms like SHA-256, is recorded in a secure measurement log stored in tamper-resistant hardware such as a trusted platform module or trusted execution environment. These measurements create a verifiable record of what software was loaded during startup. Later, this information can be used for remote attestation, where the device proves its integrity to a remote server. For example, enterprise security systems may check whether a device is running trusted firmware before granting access to sensitive corporate networks. Authenticated boot therefore enables flexible security decisions based on measured system integrity. Another major security challenge in device boot processes is the rollback attack. In a rollback attack, an attacker installs an older version of firmware that contains known vulnerabilities. Even though the firmware may be properly signed, it can still expose the device to previously fixed security flaws. To prevent this, modern platforms implement rollback protection mechanisms. For example, Android devices use Android verified boot, which stores a rollback index in secure storage such as the replay-protected memory block within flash storage. During startup, the bootloader compares the version number of the firmware image with the stored rollback index. If the firmware version is older than the stored value, the system refuses to boot. If the firmware is newer, the rollback index is updated to reflect the latest version. This mechanism ensures that devices cannot be downgraded to vulnerable software versions. Secure storage plays a critical role in protecting cryptographic keys, system configuration data, and sensitive device information. Different types of hardware storage technologies provide varying levels of protection. One common technology is flash memory or EEPROM, which is rewritable and used to store system configuration data, firmware updates, and user data. However, certain security-critical information must be stored in immutable memory. This is where technologies like one-time programmable memory come into play. Examples include EFUSE and antifuse technology, where a physical change in the hardware permanently stores data such as root of trust keys or device identifiers. Once programmed, these values cannot be modified. These secure hardware storage elements ensure that critical security data remains tamper-resistant throughout the device lifecycle. Modern mobile devices also rely on strong cryptographic protections to secure external storage. One important component is the Replay Protected Memory Block, or RPMB, which exists within eMMC or UFS flash storage. RPMB is designed to protect sensitive data from replay attacks, where attackers attempt to replace new data with older versions. This mechanism works by combining cryptographic authentication with a shared secret key stored inside the device's trusted execution environment. Whenever data is written or read from the RPMB partition, cryptographic checks ensure the request is authentic and has not been tampered with. Additionally, hardware crypto engines within the system on chip perform encryption and hashing operations using algorithms such as AES-XTS and SHA-256. These protections ensure that sensitive storage operations remain secure, authenticated, and resistant to tampering. The final layer of security in modern mobile devices is hardware-backed encryption. In this approach, encryption keys are not stored directly in software or accessible memory. Instead, they are derived from a hardware-unique key, which is embedded within the device's secure hardware. Because this key never leaves the hardware boundary, attackers cannot extract it even if they gain software-level access. This technique provides device binding, meaning encrypted data can only be decrypted on the specific device where it was created. Combined with trusted execution environments and secure boot mechanisms, hardware-backed encryption ensures that both system integrity and sensitive user data remain protected. Together, these technologies create a comprehensive security architecture that protects devices from the moment they power on to the protection of the data they store.